All right, everyone. Mr. Andrew here. So, I wanted to go over these radiometric dating practice problems because you might see a problem like this on the test. Now, these problems are actually very similar to the half-life problems, and so you're going to see a lot of similarities between these problems. So, let's go ahead and start working on them. The first problem says a parent isotope X decays into a daughter isotope Z in rock through alpha decay. The half-life of this decay is 25,000 years. Okay, I'm just going to go ahead and make a note of that real quick. Oops. I can make this nicer. T to the 1/2 is 25,000 years. Okay. A rock sample is found to contain 12.5% isotope X and 87.5% isotope Z. What is the age of the rock? So this is a very similar process to how all radiometric dating works. So what we're going to do is we're going to use the ratio of the parent isotope, isotope X, and the daughter isotope, isotope Z, to identify how many half-lives have passed. So we know that one half-life So after 0 half-lives, we have 100% parent. After 1 half-life, we have 50% parent. 2 half-lives, 25% parent. 3 half-lives, 12.5% parent. 4 half-lives, 6.25% parent. Okay? So we have 12.5% of the parent isotope, which means we've gone through 3 half-lives. So at this point, all we have to do is look at how many half-life, or how long is one half-life. One half-life is 25,000 years. So if one half-life is 25,000 years, then the rock age is equal to 25,000 years times 3. Okay? Or this is t to the 1/2. And this is number of half-lives. So this means the rock age is equal to 7,500 years. Okay. All right, let's look at the second one. So it says carbon-14 decays to nitrogen-14 through beta decay. The half-life of this decay is 5,730 years. Is this dating method effective for determining the age of dinosaur fossils, which are expected to be at least 65 million years old? Why? So this goes back to a point that was made in the presentation, and that is all these radiometric dating methods are only good for 10 half-lives, because after 10 half-lives, you have less than 0.1% of the parent left. So what we need to do is we need to take the half-life, which is t to the 1/2 is equal to 5,730 years. Okay. And then we need to multiply it by 10. So 10 times t to the 1/2 is equal to 10 times 5,730 years, which is equal to 57,300 years. Okay. Now, the age of these fossils is expected to be 65 million years old. So, is this an effective method? No. And the reason is all carbon-14 will decay before age of sample. Okay. So basically, if you had a dinosaur fossil and you tried to do carbon-14 testing on it, you would find that there would be almost no carbon-14 in there. And the reason is it's just too old. Okay. So by now, all the carbon-14 in the sample has been converted to nitrogen-14. And so as a result, it's not an effective testing method for it. Okay. So again, it can only survive, it only works for 10 half-lives. Okay. Last one, uranium-235 decays to lead-207 through a process that has a half-life of 710 million years. Okay, so T to the 1/2 equals 710 million years. Okay. When a rock sample is analyzed, it is found to have 8 atoms of uranium-235 and 504 atoms of lead-207. What is the age of the rock sample? So we need to figure out what percentage of the sample is lead-235. This is our parent, right? And this is our daughter. Okay. So if we were to rewind time back to the very start, all 504 of these atoms of lead-207 would be part of uranium-235. So we need to figure out what percent of the parent is left over. So to do that, we're going to take the number of parent atoms divided by total atoms because remember that all of these atoms used to be uranium-235. So the total will be how many atoms of U-235 were there at the start. And then we're going to multiply this by 100. Okay. So this is going to mean that we have 8 divided by 504 plus 8, that's 512. And then times 100. Okay. We get out our handy dandy calculator. 8 divided by 512 times 100. This is 1.5625% parent. Now, if we look back up here at our chart, we stopped at 4 half-lives, but we can continue this, right? At 5 half-lives, we have 3.125%. At 6 half-lives, we're going to have 1.5625. So we've undergone 6 half-lives. Okay. So all we have to do now is take the age of the half-life times the number of half-lives, and that'll give us the age of the rock. So the age of the half-life is 710 million years. And there's been 6 half-lives. So 710 million 7 times 6 is 42. 6. And then 1, 2, 3, 4, 5, 6, 7. The answer is 4,260,000,000 years. This is the age of the rock. Okay? So, it really depends on what you have given to you. Okay? In this first one, we're straight up given the percentages, so it's a little bit easier to calculate this out using the chart. Okay, I made this chart just by dividing it by 2, dividing by 2, dividing by 2 over and over again. The second one is more of a question right here and requires you to remember that 10 half-lives is the limit. And then this one right here, we're looking at needing to know the relationship between the amount of parent and the amount of daughter atoms, and then calculating out what percent of the parent is left over. Okay. Hope this helps you out. If you have any questions, feel free to ask, and I will see you next time.